Hello everyone, I want to welcome you to trigonometry, and we're going to start with section 1.1, and section 1.1 is angles, degrees, and arcs. Now the first few pages of that section you need to read because it's a terminology, kind of like a vocabulary word thing, so that you understand what I'm talking about in this video. So I would read those things first, kind of commit them to memory, and then play the rest of this video. But the main thing we're going to do here at first is we're going to learn to change from decimal degrees, that's what DD means, to DMS, which is degrees, minutes, seconds. And we're going to learn to change from degrees, minutes, seconds back to decimal degrees. Now, everything we typically do in ordinary life is in decimal degrees. Degrees, minutes, seconds. There's a lot of that. It's kind of getting outdated in today's time. If any of you know anyone who is in the tool and die industry or in the tool and die trade, they use degrees, minutes, seconds with a lot of the things they do in that profession. Of course, our helicopters and our aviation people use degrees, minutes, seconds, as well as our nautical people on ships. So let's look at example one. And what we want to do is we're going to convert something that is in degrees, minutes, seconds, okay, degrees, minutes, seconds, to decimal degrees. And we want to round it to 3 decimal places. So 3 decimal places. Make sure you read the directions. One of the most commonly missed parts of these problems are students that do not read the directions and they round to the wrong decimal place. Okay? So the key conversion factors here is 1 degree is 60 minutes. 1 minute, of course, is 60 seconds. So these are our key conversion factors here. So notice we're trying to change to decimal degrees. So notice we already have the degrees. We have 12 degrees. So really what you have to change in this problem is you're going to have to change our minutes and our seconds. So here's what I'm going to do. We're going to be adding all this together. This will make more sense here at the end. Since 12 is already in degree form, I'm going to go ahead and write it down. Now, let's look at the 6 minutes. Let's look at that individually. All right, if I want to change 6 minutes to decimal degrees, okay, 6 minutes to decimal degrees. Well, there's 1 degree in 60 minutes. So this will cause our minutes to cancel. So this would be 6 over 60 degrees. 6 over 60 degrees. So I'm going to take 6 over 60 and I'm going to add it to our 12 down here now that it's in degrees. Alright, now let's look at our 23 minutes. 23 seconds. Okay, so there's 1 minute and 60 seconds. So use your conversion factor. 1 minute, 60 seconds. And that cancels out our seconds there. But remember, we're trying to get this into degrees. So there are also 1 degree in 60 minutes. So that cancels out our minutes. So really we have 23 over 3,600 degrees. Okay? So I'm going to add 23 over 3,600 to what we have down here. Now these are all degrees. So this would, if you add all this up, this will give us our decimal degrees. And rounded to 3 decimal places, you should get 12.106 12.106 degrees. Now that's taking something in degree, minute, second form and changing it to decimal degrees. Now let's look at it the other way. Let's take something in decimal degrees and change it to degree, minute, second. So let's look at 35.413 degrees, and let's change that to degrees, minutes, seconds. Alright, so now the first thing we're going to do is we're going to take our 0.413 degrees here, and we are going to multiply it by 60. What this will give us is this will give us our minutes. Think about what we're doing here. Excuse me on the cough. Think about what we're doing. This is in degrees, and basically by multiplying by 60 minutes, we are multiplying by this conversion factor here, canceling out our degrees and getting our minutes. Okay? So, when you do that, this will give us 24.78 minutes. Okay? Now, we want to take our decimal part of our minutes and change that to seconds. We took the decimal part of the degrees, changed that to the minutes. We're going to take the decimal part of our minutes and change that to the seconds. So 0.78 minutes, and we're going to multiply that times 60 seconds over 1 minute. 60 seconds over 1 minute. So just multiplying by 60. So we're going to take our 0.78 here, and we're just going to multiply it by 60. And that's going to change it to seconds. So now we have 35 degrees, 24 minutes, and 0.78 times 60. 0.78 times 60 is, now it's going to give you we need an approximation, because it's going to give you some kind it's going to give you somewhere around 46.8 minutes. Now we don't have we're rounding just to minutes, so no need to do 0.8 of a minute. Just go ahead and round that up to 47 minutes, since we're putting it in degrees, minute, second form. And there you go. We have taken something in decimal degrees and changed it into degrees, minutes, seconds. Now the other part of section 1 has to do with angles and arcs. Angles and arcs. So let's say we have this circle here. This is point R, and this is point Q. Okay? Point R, point Q, and we're going to say point P is the center of that circle. Well, if I draw an angle from R to P and P to Q, so this would be angle RPQ. And so this is what we would call our central angle. And this green part here, RQ, is what we would call our arc. Okay? That is what we would call our arc. So here's what we say. We say that angle RPQ subtends arc RQ. It subtends or is subtended by arc RQ. We can also say that RQ is subtended by angle RPQ. So it works both ways. It's both saying the same thing. It's just two different ways to say it. Angle RPQ is subtended by arc RQ, or arc RQ is subtended by angle RPQ. Now, what's the important part about this is there's a relationship between the central angle and the arc, okay, by using the circumference to get a degree measure. So, for instance, the circumference all the way around the circle is 360 degrees. Okay, we know that all the way around the circle, 360 degrees. So, what we can say is if we draw an arc 1/4 of the circumference, we know that that's 90 degrees. If we draw an arc 1/2 of the circumference, we know that that's 180 degrees, and so on. So there is a direct relationship here between the arc and the circumference using the central angle. And this is what we say. Okay, the central angle theta, we're going to call this theta. The central angle theta is to 360 degrees as the arc length, S represents arc length, is to the circumference. Okay, this is our formula. Theta is in decimal degrees. S and C are in the same units. S being arc length, C being circumference. So, let's look at a problem. So suppose this is the center of the earth, and we know that there is a central angle drawn out between two cities on the earth. Okay, city A, city B. And this is the central angle between the two cities. And we know that that distance between these two cities is 500 miles. It's 500 miles. So, what is the circumference of the earth? So what we can do here is we can take the arc between two cities, 500 miles, this is our arc length, and the central angle made by those two cities to the center of the earth, so this is our theta. We can take that and we could actually, folks, now I know this is hard for you to believe, but we can take that little bit of information right there and we could actually find the complete circumference of the entire earth. We could find the complete circumference of the entire earth using our formula here. So what time we'll do that? My central angle, and that should be 7.5 degrees, not 75 degrees, I'm sorry. Our central angle is 7.5 degrees. We know our arc length is 500 miles. So we can find the circumference of the earth using this proportion. So this little part is to the whole degrees, as this little part is to the whole circumference. So think of it like that. So cross multiply and divide, and you will get your C to be approximately 24,000 miles. 24,000 miles. Now, if you were to calculate the circumference of the earth today, it's 24,875 miles. So that's a pretty good estimate. Now, what I didn't tell you is that this little formula that we just used to find the circumference of the earth, this was done by a Greek philosopher in 240 BC. So in 240 BC, Eratosthenes is his name. You don't need to know his name, but in 240 BC, okay, he knew the distance between two cities, and using sunlight, he got this subtended central angle, and he estimated the circumference of the earth in 240 BC. Now today, with all the high technology and equipment, it is not very hard at all to find the circumference of the earth. And the actual calculated circumference of the earth today is this. So notice, this guy in 240 BC without any computer equipment was pretty close to finding the circumference of the earth using our proportion here. Okay? Using our proportion. So, let's look at another one. Let's look at how large an arc is subtended by a central angle of 6.23 degrees on a circle with radius 10 centimeters. So first things first, we're trying to use our proportion, obviously, to solve this. Okay, so here's our proportion. And we're trying to find the arc length, evidently, by the question here. Okay, so we know the central angle. There's that. Now, here's my question. What is the circumference? It wasn't given to us, was it? The circumference of the circle was not given to us. But this little information here was. Radius equals 10 centimeters. This is where your high school geometry is going to come in, because circumference is the same thing as 2 pi r. So really, we can still find the arc length here. This is just 2 pi times 10. 2 pi times 10. So if you cross multiply and divide all that, you should get an arc length of 1.09 centimeters. Because remember, arc length and circumference are in the same units. So it's going to be centimeters. Okay, so don't mold yourself into a box. Don't get confused if they don't give you the circumference. Look at radius, and sometimes they might give you the diameter. The radius is half the diameter, and you would still use this formula to solve for your circumference. So keep that in mind as you are going through these problems. This is just an outline. This is a template formula. You can use what you already know to manipulate it a little bit. That's going to be the key to this whole class, is how well you can manipulate formulas, and you'll see what I mean later on. Alright, so one last problem, and we'll let you get to the homework on this section. Excuse me, I'm sorry about that. Alright, so here's the Earth. Here's the Sun. Okay? So let's suppose that the distance from the Earth to the Sun is 93 million miles. The distance from the Earth to the Sun. Okay? What I want to do is I want to find the diameter of the Sun. I want to find the diameter of the Sun. So think about what diameter is. Diameter would, of course, be this distance across the circle. I want to find the diameter of the Sun if it's subtended by a central angle of 31 minutes 55 seconds. Okay? So, essentially this is what this means. The Earth and the Sun form a central angle. This is your theta. And theta is 31 minutes 55 seconds. Well, and we want to find the diameter. Now, what does this diameter represent here? This is diameter, but this diameter is also, in this particular case, the arc length. It is also the arc length with this central angle made with the surface of Earth. Okay? So it would also be our arc length. So, first things first, theta has to be in decimal degrees. So take your 31 minutes 55 seconds, use our conversions like we did before, and get it into decimal degrees. Okay? So this will be a good chance for you to practice that. So we have our formula here. Alright, so they've given us theta, so that's pretty easy. No biggie there. We're looking for this diameter. This diameter is the same thing as our arc length. So we're looking for the arc length here. Well, what about circumference? Nothing was said about circumference in there. Most common error is people think this is circumference when it's not. Okay? Think of the solar system as a whole. The distance between the sun is the center of the solar system. So the distance between Earth and the sun would be the radius. That's what they gave you, is the radius. So we would have to use 2 pi r for our circumference here, and take our 93 million and substitute it in. So really, this is what we have. And please get in the habit of not rounding in trigonometry until the very last step, because if you round before the last step, it's going to cause you to have some error. So, cross multiply and divide, and you should get somewhere around 864,000 miles for the diameter of the sun. Because remember, that arc length represents the diameter here because of how our Earth is, because of how the Earth is forming that central angle with the sun. So the diameter and arc length of the sun are one and the same. Okay? We call it the intercepted arc and the chord. That's the geometry rules for it. You can read on page 9 and see and get more of a definition of that. But essentially, the intercepted arc is the arc opposite the central angle. So here's our central angle. So this right here would be technically called an intercepted arc. It would be called an intercepted arc. It's the arc opposite the central angle. And the chord is a straight line joining two endpoints. So this right here would be our chord. This diameter would be our chord, the straight line joining two endpoints. Okay? Alright, so hopefully that's understandable. That's section 1.1. And check back soon. You'll have the next section available for you.